Hey Pre-Calc students, in this video we're going to talk about polar equations. So we've been studying the difference between polar and rectangular function or points, and today we're going to talk about polar and rectangular equations. So the first thing that I want to point out is that a rectangular has points x and y, and their equations are x's are the inputs and y's are the outputs. Here's an example of a rectangular equation defined by x's and y's. This would be a positive quadratic, and when you graph it, we know that it looks like a U shape. For polar, points are defined in r's and thetas, so the equation is r is the output and theta is the input. So polar equations are dependent on theta and r is the independent variable. So there's a reason why we have both systems, and that's because some functions are easier to graph in Cartesian and others are easier to graph in polar. So really quickly we're going to talk through some of these, but here are some examples of polar equations in what are called Cartesian or rectangular equations. Here we've got r equals cosine of theta equals 2. R cosine theta equals 2. That's the polar equation of the same equation x equals 2. Both of these, when graphed, would look like a vertical line. One's just in polar format and the other one is in Cartesian. The second one gets a little bit more complicated in polar. R squared times cosine of theta, sine of theta equals 4 is the same function as x times y equals 4. And so forth. So sometimes they are really complicated, like this one in polar format, but the Cartesian format is not as bad. So we want to be able to transfer back and forth between polar and Cartesian. So here, for example, r equals 1 minus cosine is a very simple polar equation, but then the equivalent x and y equation becomes quite complicated. So again, we're going to learn how to convert back and forth. How do we take something that is polar and turn it into Cartesian, and something that is Cartesian and turn it into polar equations? Whenever we're converting equations, just like converting points, we want to use the same four basic formulas. So the four basic formulas that we've used so far are the x squared plus y squared equals r squared. Tangent of theta is equal to y divided by x. Y can be replaced with r sine theta, and x can be replaced with r cosine theta. So for my first example, we are going to convert x squared plus y squared equals 9 into a polar equation. So what we've got here is a rectangular equation defined in terms of x's and y's. Well, what we want to do is use one of our basic equations and see, one or more of our basic equations, and see if we can convert it into r's and thetas. The first thing that I'm going to point out is that I've got this x squared plus y squared here, and I also have this x squared plus y squared here. Well, since over here we know that the x squared plus y squared is equal to r squared, then I can replace any x squared plus y squared with that r squared. So that's the first thing I'm going to do. Instead of x squared plus y squared in my original equation, I'm going to write it as r squared equals 9. In just a moment, I'll show you graphing technology that we can use to graph both the original rectangular equation and the polar equation. But one thing that we will need in order to be able to graph a polar equation is to solve for r. So to get r alone, I'm going to take the square root on both sides. So r is going to be equal to the plus or minus 3. In other words, I have two equations that I can use to represent the same rectangular equation with the polar equation. Let me get a Desmos and I can show you that Desmos can graph both the original rectangular equation and the polar equation. Okay, so the first thing I'm going to show you is the original rectangular equation, x squared plus y squared equals 9. You might remember this from Math 3, that this equation is an explicit form of an equation of a circle that has a radius of 3. So we have x squared plus y squared equals 9 is a circle with a radius of 3. Now what I'm going to do is I'm going to ungraph that, and I'm going to graph both r equals 3 and r equals negative 3. When you see that r equals 3 and r equals negative 3, you can see that it is also both of them are circles with a radius of 3. So these are going to match the rectangular equation, because again, we are talking about the same exact graph, just in two different systems, a rectangular system and in polar. The last thing that I'll show you in Desmos is that Desmos does have polar graph paper versus rectangular graph paper, and you can find that in your settings by switching between rectangular and polar graph paper. Again, the main thing with converting is always finding something to replace. So for this problem, we've got x squared plus y squared equals 9 times y divided by x squared. And so we want to be looking for things that can replace. Since we know x squared plus y squared can be replaced with r squared, that's the first thing I'm going to do. R squared is equal to 9 times y divided by x squared. And we're not finished until we have replaced all of our x's and y's with either r's or thetas. So the second thing that I'm going to notice is this y divided by x. I can use this identity right here, tangent of theta is equal to y divided by x. And I can go in and replace this y divided by x with tangent of theta. That's still being squared, the 9 is still there, and it's still equal to r squared. Again, just like before, if it's easy to solve for r, we should do so. So to get r alone, we'll take the square root. So r is equal to the square root of 9 tangent of theta squared. This can be simplified a little bit, and I can simplify this by saying that r is equal to the plus or minus the square root of 9, which is 3, and the square root of tangent squared, which is tangent of theta. Just to check my work, I am going to use Desmos to graph the original rectangular equation and the polar equation and see if they match. Okay, I have my original rectangular equation, and it looks like this kind of double-sided U shape. And then if I graph r equals 3, and I'll just do one of them, so 3 tangent, and then I have to use theta. Again, if I wanted to make sure that it is truly graphing polar, I need to use the variables r and theta. So I'm going to use r equals 3 tangent of theta, and the graphs do line up. So again, we have converted correctly, and it would also be true if I made this a negative out front as well. It's going to still be the same graph. One is rectangular, one is polar. Okay, for my next example, I've got 3y minus 7x equals 10. So this problem, I don't have x squareds or y squareds. I don't have y divided by x. So the two ones I'm going to be looking at are my y equals r sine of theta, y equals r sine of theta, and x equals r cosine of theta. So whenever I see a y, I can replace that with r sine. So this y here is going to get replaced. And whenever I see x, I can replace that with r cosine. So I'm going to go through and I'm going to carry the 3. And I'm going to have, instead of y, r sine of theta minus 7, and instead of x, I'll have r cosine of theta, and that's going to equal 10. If you can remember, our goal is to solve for r. Usually our polar equations, it's best to get r alone. So I'm going to actually factor the common factor of r out. So this will be, when I factor r out, I'll have 3 sine of theta minus 7 cosine of theta, and that's equal to 10. And then to get r alone, I just have to divide by 3 sine theta minus 7 cosine theta. So r is equal to 10 over 3 sine theta minus 7 cosine of theta. Okay, so the next couple examples that we'll do, we'll see how long we have, how many we can get through. We're going to talk about how do we convert from polar to, converting from polar equations to x's and y's. So here we have r equals 4 sine of theta, and we want to be able to change this in terms of x and y. So the first thing that I'll notice is I don't really have any place in any of my formulas where r is alone. So the left side of this equation is not an easy substitute. I also have a sine of theta, which I can see here, but I need an r on that side in order to be able to replace it with y. I need an r there. So what I'm going to start this problem off doing, and this is a pretty common tip, is we're going to multiply both sides of my equation by r. This is allowed as long as you do one thing to one side of an equation, as long as you do it to the other. It's an acceptable operation in the equation. So I'm going to multiply both sides by r. When I do that, I can simplify. My left side of my equation is going to be r squared is equal to 4 times r times sine of theta. And so now I can identify some pieces that I can replace. This r sine of theta can get replaced with y. So this will be 4 y. And my r squared can be replaced with x squared plus y squared. So this r squared here can get replaced with x squared plus y squared. And we will actually leave this problem like this. And we can do that because we're all in terms of x's and y's. Okay, so that's actually, this next problem is very similar to the one that we just tried. I'm going to give you guys an opportunity to try this one on your own. So pause the video and see what you can come up with. Okay, first I multiplied both sides by r, making sure I distributed to both the sine of theta and the cosine of theta. And then I had an r squared, so I replaced that with x squared plus y squared. I had an r sine of theta, so I replaced that with y. And I had an r cosine of theta, so I replaced that with x. Okay, the last problem that we'll do, and this is the last hint that I'll give for converting equations, is whenever you have a denominator for a polar and you're trying to convert, another helpful hint, similar to multiplying by r on both sides, is to actually get rid of your denominators. So in this problem, if I want to get rid of my denominator, I can multiply the denominator on both sides of the equation. And when I multiply, I'm going to fully distribute that r times the denominator. On the right side of the equation, the denominator and what I'm multiplying by cancel out, and I'm left with just 5. From here, I can do my replacements. I have my r sine of theta, which is a substitute for y, minus 2 r cosine of theta, which is a substitute for x, and that's going to be equal to 5. Since my equation is fully in terms of x and y, I have converted from polar to rectangular. Again, I can check the original graph of the polar and the rectangular to see if they match, to see if I've done it correctly. One last thing that I'll say about the denominators is sometimes the denominators are hidden. This is not an example that I'm covering in the video, but just so you can see, if you had an example like r equals 5 times the cosecant of theta, Well, if you remember from our identities, cosecant is the same thing as 1 over sine of theta. So if I use that reciprocal identity, then I have a denominator that I could multiply on both sides. So whenever you have one of your reciprocal identities, sometimes it's nice to use those in order to have appropriate substitutes for x and y. Okay, that's it for this video, and go give the practice a try, and we'll do more practice with this when we meet in class.